Good morning, children. In this video, I will be explaining variation of ionization enthalpy in D block elements. So, all possible questions I will be covering in this video. So, please watch the video till the end. Right? Now, first, let's understand what is ionization enthalpy. So, you can define ionization enthalpy as the minimum energy required to remove electron from valence shell of neutral gaseous atom. This is very important, children. Most of the time you forget that you have to remove from the neutral gaseous atom. Neutral is only when I am talking about the first ionization enthalpy. Otherwise, it can be from a cation, one unipositive, that is second ionization energy. So, we will be discussing it. So, when we are talking about the first ionization enthalpy, we are removing the first electron, that is always from a neutral gaseous atom. Okay, now how does it vary in the D block element? That is what we are discussing. Now the first thing is that the ionization enthalpy depends majorly on two factors which you have been studying in periodic classification also, that is the atomic size and nuclear charge. But as far as the D block elements are concerned, there are number of factors because the last electron here doesn't enter into the valence shell. It's entering into the penultimate shell. Right. So what exactly are D block elements? Let's understand that part first. Say this is the nucleus, first shell, second shell, third and fourth. I'm talking about fourth period, that is 3D series. So 4s2 is filled and then the electron starts going into 3D. Right. So first thing is when the size increases, then the distance between the nucleus and the valence shell is increasing. Size increases, the distance is increasing. So the hold of nucleus over the valence electron reduces. So when size increases, ionization enthalpy has to decrease. That is generally in all the groups, in all the period. Right? Size increases, ionization enthalpy is decreasing. Now, nuclear charge, more the nuclear charge, the ionization enthalpy should be increasing. So first what I am explaining is the general aspect. Then how will it vary in particularly D block elements we'll be talking about. Shielding effect. Shielding effect is when the electron is added, the last electron in the D block element is coming in the penultimate shell. That is this shell. The valence is fourth, but the electron is going into 3D. So this is forming a shield between the nucleus and the valence electron. So when more and more electrons are added in the anti-penultimate shell, in the penultimate shell, not anti-penultimate is in case of F block. So when the electron is added in the penultimate shell, that is these, then the shield is increasing. So in a way what you can say is more the shielding effect, the ionization enthalpy should be decreasing. More the shield means more the electrons coming in between the nucleus and the valence shell. So the hold of nucleus over the valence will decrease. So ionization energy should be increasing. Right? So more the shielding effect, lesser is the ionization enthalpy. Something is coming in between the nucleus and the valence shell. So hold of the electron will decrease over the last electron. Right? Now this is something different, reorganization energy. Now what's reorganization energy? Let's understand that how the electrons are being filled in D block. You have say 4s first, right? There are 2 electrons in 4s and the D starts filling. This is 3D. So after 4s only the electrons start going into 3D. So there are 5D orbitals. So let's suppose there are 3 electrons here present in D. So what happens in the D block elements is when the energy is provided to the neutral gaseous atom, the first electron will go from the valence shell. So energy is provided, electron will go from here. So when first electron is going, say this electron has gone. This is no longer there, one electron has gone. One electron has gone. That means we are talking about the first ionization enthalpy. Right? So within this, D, what happens is, this electron which is left over in 4s now, this reorganizes itself to come in this one. Reorganizes. Why it reorganizes itself? Because if suppose only 3 electrons were there in D, then how many exchanges will be possible? Let me draw it here separately. 3 electrons are there. How many exchanges are possible? This can exchange with it. This can exchange with this one. And these two can exchange. That means if 3 unpaired electrons are there, the number of the exchanges possible are 3. If there are 4 unpaired electrons, then how many exchanges are possible? One can exchange with 2, one with 3, one with this, then 2 with this, then this, and these two. So total 6 exchanges are possible when there are 4 unpaired electrons in D. So if first electron goes from 4s, the next electron reorganizes itself. That means this electron goes to this d orbital and it prefers being there because there is more exchange energy if there are 4 unpaired electrons. It is more stable if more exchanges are possible. So we say more the exchange energy, more will be the stability. So it prefers being stable. It prefers being having more exchanges. Right. So suppose we say 50 kilojoules per mole is the energy required for excitation. 50 kilojoules per mole is required for the excitation of the electron. The atom will say absorb around 55. Out of 55, maybe 2 kilojoules are required for reorganization. The extra 3 are given out in the form of the exchange energy. That means there is not only the ionization energy, that is the energy required to remove electron within the d orbital, there is reorganization also happening, which will result in more number of exchanges. More the exchanges, more the exchange energy released. This is required energy, this is released energy. More the released energy, more is the stability. So within the atom, there is exchanges happening to make it more stable. So there are all these, these all factors are responsible for the overall ionization enthalpy. That is why what we find is in the d block elements, lot of variations in the ionization enthalpy. It doesn't follow, the normal trend, like it is across the period. In d block elements, we don't talk about the ionization enthalpies this way, that is down the group. We normally consider is across the period. So across the period, the size decreases. Size decreases means the ionization enthalpy should be increasing. But we saw in the previous videos that the even atomic radii, that is size, is not varying uniformly. It's not decreasing uniformly. Okay, so now let's consider like how the ionization enthalpy would be varying across the period. Okay, now children, let's consider the next point. It said that first ionization enthalpy of d block element is greater than s block and less than p block. This I think you can follow because you know the position of the p block and s block with respect to d. D is in the center. On the left hand side you have s block, on the right hand side you have p block. And across the period what happens to the atomic radii? Atomic radii is decreasing. The atomic radii is decreasing, that means the d block elements have lesser size than s block. They have lesser size means so the ionization of d will be obviously greater than s. What about p? P is still smaller. P is smaller than d block. So d block will have lesser ionization enthalpy as compared to p block elements. Fine, this can be directly related to the size. Now within the d block, how does the ionization enthalpy vary? To understand that, we will have to consider like how is the atomic radius varying in the d block elements. This is 3D series I am writing. 3D series. 3D series scandium, titanium, vanadium. We find that across the period, what happens to the atomic radius? Let's write that first. If I am talking about the atomic radius, from here scandium to manganese, the atomic radius decreases. Then we find that iron, cobalt, nickel, they have nearly the same radii. That how radii varies, we've already discussed in the previous video. Please check that out. And across the period further towards the end, copper and zinc, they are found to have more atomic radii. So with reference to the atomic radii, from scandium to manganese, atomic radii decreases. Iron, cobalt, nickel, it's the same. Copper and zinc again have more atomic radii. So keeping that in mind, we will have to consider the ionization enthalpy. Overall general trend is across the period ionization enthalpy is increasing. That is for sure. We have already spoken about it, that across the period it has to increase. But there are a lot of exceptions. Why there are exceptions? Let's first consider the trend, how the ionization enthalpy trend is. From scandium to vanadium, the ionization enthalpy is found to increase. In chromium, the ionization enthalpy is found to be comparatively less. And Mn, again, it's found to be more. Thereafter, you find that the ionization enthalpy remains the same. And copper and zinc, though the size is increasing, their ionization enthalpies are found to be more. See, these are all exceptions. This is fine. Size is decreasing, it's increasing. What about this? This is an exceptional case. Mn, exceptional case. Copper and zinc, they are having more size. More size is because of the repulsion. But even then, bigger size, their ionization enthalpies are high. Why is it so? We are going to discuss all this just now. Just see this graph. It's between ionization enthalpy and the atomic number. What you find is, with the increase in the atomic number, the general trend ionization enthalpy is increasing. In all the series, first, second, third series. So, you can observe in this, there are some exceptional cases, right? So, in 3D, there are many exceptions. And you find that the third series has the maximum ionization enthalpy. So, that is the greatest. Down the group, actually the ionization enthalpy should decrease, but the 3D has the least and the 5D series have the maximum ionization enthalpy. What is the reason for all this? We are going to discuss in the video. See, these are the all questions which we'll be answering. The first is the successive elements have less energy difference. That is ionization enthalpy difference. Successive elements, that is if you compare the values, scandium, titanium, vanadium and all that, the difference is very less as compared to the other groups or other periods. The reason for that is the participation of Ns and N-1d, in which the energy gap is very, very less. The energy gap between the two is very, very less. Okay. The next thing is that the first ionization enthalpy of chromium is less. To answer all these questions, we should be, taking care of their configurations. So, chromium configuration is 4s1 3d5. Of course, argon is there. So, we are writing the main configuration. The first electron. So, when first electron is removed, it's able to get the the half-fill configuration. It's able to get half fill. Even now it is half fill. But even after losing one electron, its stability is not getting affected. So it doesn't mind losing one more electron. So it can be, considered that the first ionization enthalpy of chromium is very less because of half-filled configuration. You will write that it is already half-filled and even after losing one electron, it is not losing its stability. So the first ionization enthalpy of chromium is less. This can be a question asked in board. Then let's talk about the second ionization enthalpy. It's observed that the second ionization enthalpy of chromium is more than vanadium and even manganese. Because after losing one electron, it acquires 3d5 configuration because one electron of S has gone. Now it is this. Mn otherwise is Mn before losing electron is 4s2 3d5. So after losing one electron, it will be 4s1 3d5. So again it can lose one more electron readily. And this before losing electron, it was 4s2 3d3. So even this is not in comparison to chromium. So chromium, after losing one electron, acquires valence shell mein, now that is 3D mein half filled, so it is very, very stable. Next we come on to the third ionization enthalpy of manganese is very high. Just now we wrote that this is Mn configuration. Third ionization means those two electrons are already lost. So Mn, which was already 4s2 3d5, now after losing two electrons it has formed Mn2 plus, wherein its configuration is 3d5. Now it is 3d5, means it's very stable. It will not like to lose one more electron and become Mn3 plus, because this is already stable. So third ionization enthalpy, that is now removing from Mn2 plus. Third means removing from 2. Second means removing from 1. So that is, this 1 means plus 1 charge. Okay, so this cannot lose further because it is already stable half filled configuration. Okay, now let's move on to the other set of questions. It says the first ionization enthalpy of iron, cobalt, nickel are same. The reason being their atomic radii are same. Same atomic radii, so their ionization enthalpies are also the same. This is a simple thing, right? First ionization enthalpy of copper is low, whereas the second is high. Let's write copper configuration. Copper configuration is 4s1 3d10. Right? So first ionization means removing electron from the neutral atom. After losing one electron, it will become Cu plus, and now its configuration becomes 3d10. So again it's the same thing like Mn. It is already stable in D10. After losing its stability is not getting affected, so it can easily lose one electron and become 3d10. Now once it is 3d10, to become this, it's not possible because it will not like to lose its stability. Got it? The next comes the first ionization enthalpy of zinc is high and the second ionization enthalpy is low. Please children, I am repeating again and again, you need to answer all these questions with reference to the electronic configuration. So zinc configuration is 4s2 3d10. So it's already stable. It is stable means after losing one electron it will be Zn plus. So it will not like to lose electron. 4s1 3d10. It is this also 10, this is also, this is actually having a pseudo inert gas configuration. This is 18 electron configuration, pseudo inert gas configuration, so it will not like to lose its stability. Now after that, to acquire this, it is not getting affected now because it has to form this, which is 3d10. So don't say it is 3d10 here also. This 4s2 3d10 put together is a pseudo inert gas, so it is not happy to lose that configuration. Okay, now after losing one electron it has formed this. Now if it still loses one more, it will be 3d10. So in 3d it is 10 here as well as here, but this 4s1 is not a pseudo inert gas configuration. Got it? Moving on to the last two questions. The third ionization enthalpy of Fe is low. Let's write Fe. Fe is 4s2 3d6. Third ionization. So first ionization it will become Fe plus. Fe plus means 4s1 3d6. Now after that, this is the first ionization enthalpy. Now in the second ionization enthalpy, it will become Fe2 plus, which will be 3d6. Okay, so they are saying the third ionization enthalpy is low, means it will be happily losing one more electron to become 3d5, that is half filled configuration. Okay, so it will lose one more electron readily so as to get half filled d orbital, which is very stable for it. Got it? Now the last question is that the first ionization enthalpy of 3d third transition series is much higher, which I showed you in the graph. Right, for that let's understand their positions. Scandium, titanium, vanadium. I'm just drawing a part of these elements, that is a series. Next comes here is here, sir, no. Here it is lanthanum, Okay, so this is 3D series, this is 4D series, this is 5D. This is first transition, second and third. Down the group, ionization enthalpy should be decreasing, but this has comparatively high ionization enthalpy than first and second that we saw in the graph. The reason being, this is 57 atomic number, this is 72. Between them, that is 58 to 71, there are lanthanides present. And in lanthanides, you know that the 4f orbital is being filled. 4f orbital is filled in lanthanides which has poor shielding. They have poor shielding because of the complicated shape of the f orbital. There is poor shielding. So because of poor shielding, the effect of the nucleus over the valence electron is more. Even in all the post-lanthanide elements, that effect of the lanthanide contraction is visible. So because of the lanthanide contraction, all the post-lanthanide elements have comparatively smaller size, due to which their ionization enthalpies are higher. So it's like the third transition series have more ionization enthalpy than first and second. Okay, I hope you have followed. All your queries are clear for regarding the ionization enthalpies. In the next video, children, I'll be explaining oxidation states and the electrode potential variations. Okay, thank you.